There are four main types of user variables. You can name them whatever you'd like. If you want, you can just address them by their variable type and a number, or you can give it a name that actually means something. The first one is global variables. They're generally your P variables, P1, P2, P3. There are 536 of them. They are double precision, as are most of them, honestly. And global variables can be accessible pretty much from anywhere inside of a PMAC. Script, C, pretty much whatever you're doing, online commands, the terminal, motion programs, PLCs, they're as global as it gets, basically. The next one are coordinate system global variables. They are stored as Q variables. Again, they're double precision, so 64-bit floating point. And they are global to within a single coordinate system. So the main use of them is going to be if you have a motion program that wants to grab a spindle speed, say. So inside of each of your coordinate systems, you'll define Q131 is your spindle speed QVar, and then you can just, inside the motion program, set the speed of axis A is equal to spindle speed QVar. And if you run that in motion program 1, that might give you 5,000 RPM. Motion program, or coordinate system 1 might give you 5,000. Coordinate system 2 might give you 3,000. It's just a way for you to have the same Q variable, same global variable, inside of multiple different coordinate systems with different values in each coordinate system. So your motion program can just grab a single variable, and the value will change depending on which motion program you run it, so it varies depending on machines or subsections of a machine, depending on how you've defined your coordinate systems. The next ones are pointer variables. They are M variables. They generally could be 64-bit floating point, but they're basically defined as whatever it is you're pointing them to. They will point to a memory location on the PMAC, and they are probably one of the more versatile ones. They're suggested M variables that we already have set up for you, but in addition, you can point an M variable at a scratch register and just do some calculations, stick it there, and access it from wherever you want. Or you can point it at something that we are internally calculating, but we may not have a predefined easy way of accessing. So a lot of status bits will be M variables pointed at a specific bit of a given register. So you query that M variable and it'll just read that specific bit for you. Last ones are local variables. They are local to whatever PLC, coordinate system, online command, wherever you're calling them, they're pretty much local to that. That's their scope. Again, double precision, 64-bit floating point, and they go away as soon as whatever called them finishes. So if it's a PLC, when the PLC ends, local variable will go away. To declare them for a P variable, global variable, you'll typically do something like this. You can have global and then the variable name. You can also do an array, as shown by my global array 10. You can set it to a value right off the bat by just global variable name and then set it equal to whatever you'd like. And that's generally the format for pretty much all of them. Just change global to CS global, or in this case here, local. For Q variables, again, same idea, CS global and then variable name or array name and the size of the array. You'll, for those in particular, generally have the same variable in multiple different coordinate systems with different values in different coordinate systems. It's one way of even just identifying what coordinate system a motion program is running in. You can have a CS global value set to coord sys or something like that, and set it equal to 1 in coordinate system 1, 2 in coordinate system 2, and you can have a PLC or motion program query coord sys to find the coordinate system it's running in. There's a different, faster way to do that exact action that we'll see in a little bit, but just as an example of one possible use of these. If you want to call one from the terminal window, generally terminal window will go to the currently addressed coordinate system. You typically don't address coordinate systems in the terminal window, so it'll usually default to 0, but if you want to, you can query a specific one from inside of a specific coordinate system like this by issuing ampersand coordinate system number and then whatever the variable name and it will return that value for that variable from that coordinate system. So in order to declare pointer variables, because they're not really normal variables like the P, L, and Q are, you would do some definition like one of these two lines here, where you'll have either M and then the M variable number, then you'll have dash greater than, so points to in this case, and then here we're doing format.io colon address offset, possibly .start, possibly .width. That makes a lot more sense than an example, so we'll get to that in the next page and show you what you actually fill in those with. But you could, if you don't want to address it as an M variable number, you can declare pointer, your variable name, and then same thing, dash greater than, and then format.io, address offset, start width. Let me skip ahead really fast just to show you what that looks like. We have this line here where we're having a pointer named input1, and it's looking at gate.io 0, data register 0, and it's starting at bit 0, so the very first bit of that register, and it has a width of 1 bit long. So this input here will look at a total of 1 bit. It'll be bit 0 of this memory location. So if you're in the I/O space, it'll be format.io. If you're in user shared memory space, it would be .user. You can also have self-defined ones that you'll need to use if you're doing an array. You'll need to, for an array, first just self-define it, and then you point each individual element in the array to its own spot. But to do that, you'll just do M constant or pointer variable name, and then points to asterisk. And if you want, you can have the format of it and you can have the width of it, but generally you just point it to an asterisk and that will define that M variable. Now for that format, if you want, for this blank.io or blank.user, you have a couple of different options. You can choose a signed integer that saturates at a maximum value. That'd be an s.io or an s.user. I.io or .user would be an integer that rolls over and starts back again. You could have an unsigned integer that rolls over. You can set it to a short floating point, so that'd be f, or a long floating point that'd be d. It should be noted that for those two, because it's being set to a 32-bit floating point number or a 64-bit floating point number, you don't input the start or the width. You only point to the address, and it will just take the value of that entire address. For start and width, you have the options of 0 to 31 for the start point. That's because you can look at any of the 32 bits in the register as your start point. For width, you have 1 to 32 because you are going to look at least 1 bit of it, and you may look at up to all 32 bits of it. So if your start is going to be 31, in reality, you're only looking at 1 bit because you can't go to more significant bits than that. You're already at the most significant bit in the register. So your range for width is really only 1 through 32 if your start value is 0, but the maximum width will shorten as your start value increases. So some examples. In this case, the first one here, pointer, my pointer, is pointed to *i.16. So it is a self-referenced pointer. As of now, it's not pointing anywhere in particular, but it is a 16-bit signed integer with rollover. So when we do point it to a register, or when we do point it to whatever it is, that will be the form of the data. The next one we already briefly went over. Its input 1 is pointing to gate.io0.dataregister0.0.1. So it's looking at the first bit of gate.io0.datareg0. That would be a fairly typical one if you're just trying to access data from an I/O card, like if you have an accessory 11E or 68E. That should be one of these cards in your box, probably right next to the 24E3 you have. From the front, it basically has 2 lines of LEDs, 2 just vertical lines of LEDs, and as I/O bits turn on or off, the LEDs turn on or off. So we'll be using those a little bit later today. Next, you can do something like, well, pointer to alt input 1 goes to u.io, and then it looks at that address, $A0000000, 0.0.1. So it goes to that address in IO memory and then grabs the least significant bit of that specific register. In this case, we have M100 points to sys.servocount, which is just to say that M100 will now be a quicker way to grab an already named value, an already named parameter such as sys.servocount. You can do an array like pointer points to outputs 4, or pointer outputs 4 points to asterisk. The 4 in the parentheses there says it's going to be a 4-element array. Points to asterisk basically just says that it's a self-referencing array currently. And then you'd go through with the next 4 lines here and define what each of the individual elements are. So they're saying output 0 points to getIO0, datareg3, 0, 1. So the first bit of getIO0, datareg3. Outputs 1, same thing. It's still only 1 bit long, but this time it starts at bit 1. So this would be the next bit. And then outputs 2 and output 3 are the next 2 bits sequentially. You'll notice that all 3 of them have a width of just 1, or all 4 of them have a width of just 1, so they're only 1 bit. But the starting bit increments from 0 to 1 to 2 to 3, depending on which bit in particular it's looking at. And then at the bottom here, we have pointer user shared memory pointer 1, 2, and 3, pointing to u.user, and then pointing to $408, $488, 416.8. We'll get into that a little bit later in this section, but that's for user shared memory, and that's accessible from sys.udata1 bits 0 through 7, bits 8 through 15, bits 16 through 23. Now, when you assign a variable or assign a pointer, it will, if you give it a name rather than a number, start by giving it a number internally to PMAC. So if you define global, my global var, it will give you a p variable, corresponds to that, and it will start at some somewhat arbitrary number. By default, it's 8192, P8192. Just we figure that's sufficiently high as to be unlikely that you're using it. However, if you want, you can choose in the IDE what number you actually want it to start with. The way you do that, I'm going to do it really fast, is in the IDE, if you go to your project name and then go to the properties window, we see I have M variable starting point, P variable starting point, and Q variable starting point. They're set to 8192, 8192, and 1024 respectively. If I wanted, I can change this to 3000, say, and now the first M variable I define as just having a name rather than defining it as M200 or M whatever number I want. PMAC will take my variable name and set that equal to 3000. Then the second one will be 3001, 3002, and it will continue on in that fashion. So that's how PMAC accesses it. The PMAC itself obviously doesn't know or even care about the variable names. It cares about what number it is and what memory address it's stored in. So the IDE will take all of your variable names you're defining and replace them with appropriate numbers that PMAC can understand. Local variables, as we'll see in the next couple slides, always start at L0, just because local to the system, there's only so many of them. It's unlikely you'll be using named ones and unnamed ones. PMAC doesn't really do much calculations in them itself. There's less concern about basically hitting one that you've already defined somewhere else in the program. If you're using a P variable, you may use P variables in every PLC, every motion program, in all sorts of different spots on the box, and so it's easy to accidentally start by defining a couple of P variables over here, and then define global variables by giving them names over here, and PMAC itself uses some P variables for calculations at times. So to prevent from hitting itself and overwriting its own values, we decided to include some fairly large offset to it that's, again, user configurable. But for L variables, there aren't the same concerns, so they'll generally just start at L0. So R variables and L variables are really the exact same variable, as we'll see on the next slide. But they're two different naming conventions, and they're basically used for passing variables between programs and subprograms, or subprograms and subprograms that they call. Basically, there will be just an offset of 256 between them. So if you're using L0, that's equivalent to R256 in the same subprogram. If you use L0, though, that's equivalent to R0 in the next layer down. And the next slide will explain this better than I can, so I'm going to move on for 1 second. C variables are renamed coordinate system L variables for passing and returning axis values between kinematic subroutines. So C5 is the same as L, max number of motors, plus 5 for the coordinate system. You can address L variables from coordinate systems or PLCs using these parameters here. Same with R variables, and you can see how many total L variables there are in that given coordinate system or PLC with L index. And just to explain the LR variables thing a little bit clearer, in the top level program here, we have L0 through L255. Those are local variables to it. They have no significance directly to subprograms that it calls. In addition to those L variables, L256 and R0 are the exact same variable. So you don't want to use L variables with 256, but in this case, we also have L0 through 255 and R0 through 255. The L variables are going to be the ones that you're generally using just inside of that top level and don't want to pass to any subprograms. R variables you'll use if you want a local variable that has some scope to it that can be passed to a deeper level of subprogram. So if my motion program that I'm running has to call a subprogram that just has some function built into it, say it calculates the sum of the square of two different numbers. So I have a subprogram called sum of square, subprog. I pass in two variables, and the subprogram will do the calculations based off that. What I can do is define those values I want the subprogram to use as R0 and R1, and then inside of the subprogram, I do all of my calculations as L0 and L1. PMAC automatically links R variables of a higher level program or subprogram to the L variables of a subprogram that it calls. So an R variable in a program or subprogram is equivalent to, and it points to the exact same memory location as an L variable in a subprogram that is being called by that program. So in that case, say the subprogram needs to call another subprogram, it can use its own R variables, R0 through 255, set those, and when it calls its subprogram can access those variables by looking at L0 through L255. So this allows a way to pass local variables through to subprograms, but it does have a slight risk associated to it if you're not paying attention and you have too many L variables or too many R variables, because if this top level program has so many L variables, it goes all the way up to 700 of them. That is now overriding the R variables from this one and even the L variables from this one. So you need to be careful just to make sure you're not going above 255. If you do, you probably want to try and figure out a different way to do it. Either define them as global variables or give them some scope such that they can be accessed from the subprograms directly, because with just local variables, you will be overrunning them. Now, we talked about, and I showed you guys where you can see that when you give a variable a name, PMAC will automatically assign it to a variable number. So P variables automatically start at 8192. If you don't want that though, if you want to manually decide what p variable number is being given to that name, or vice versa, you can issue a pound define statement instead. So pound define variable name and then where you want that stored. Pound define my p variable p10. That guarantees that if you type my p var equals 5, p10 will be equal to 5. Pound define my mvar3 m200. Now my mvar3 is the same as m200. If you set one of them, you're setting both of them. It's just another way to access it. It's a simple text substitution done by the IDE when you download it onto the PMAC. And you'll generally want to use variable numbers lower than 8192 or 1024, whatever that number you have set as your starting number for auto-assign numbers. Just because if you tell the IDE to start auto-assigning at 8192, and then you manually define my pvar is equal to 8200, PMAC may try and auto-assign a different pvar to 8200, and they may fight with each other. You'll probably end up losing one of them. So, with a case like that, you want to make sure that any manually defined variables are far enough away, or are not in the range that PMAC will auto-assign. So you can have arrays of any type of variable you want. You can either just outright give the size of the array, or you can give an equation of some sort, a simple arithmetic equation, such as p1 minus p2 plus 7 in this case. That will be equal to the size of the array. They are function calls technically in the way the PMAC handles them, so you want to use parentheses, not brackets. Need be, it will round down to the next integer before using to select a particular variable. Obviously, you can't have an index 5.7 as the 5.7th element of an array. So if you try and access that, it will round it down and give you the 5th element in the array. You can use them in motion programs and PLCs in addition to online commands, depending on what it is you're trying to do. And they'll have the same scope as the variable type that they are. So a p variable array will still be a p variable, will still be global. M variable arrays will still take on the size and scope of whatever they're pointed at. Okay. So user-defined buffer memory space. This is general purpose memory that you access with these structures shown here. Honestly, this slide and many of these slides are really more reference slides and something you need to know for yourself, just because it's important to have a good spot where you can look up where memory locations are and how to define certain things, but it's not something you're going to use day to day using a PMAC. But sys.ddata 0, 1, and n. 0 is 8 bytes long starting at sys.pushm. 1 is 8 bytes long starting at sys.pushm plus $8, and it continues on. N would be sys.pushm plus $8 times n. If you wanted 32-bit rather than 64-bit, D being double, 32-bit, in this case we're going to go with floats, sys.fdata, same idea, except now the offset is going to be 4 per one because it's 32 bits instead of 64 bits. You can have idata, just 32-bit integer values. That's 32 bits, so it's also just going to be 4-bit offset between indices. You can also just access an 8-bit character for a string, and that would just be sys.cdata, and it's just a single byte long. Now, there are different ways of accessing the same register using these ones. As you see, they have various different offsets. sys.pushm plus $4 plus $8. They can overlap each other. And so if you're using multiple different ones, you need to be careful that they're structured in such a way that each is inhabiting its own clear 4, 8, or 1 bit, depending on which type you're using. And you don't have two different parameters accessing the same memory location unless it's what you're trying to do, which it may very well be in some cases. But you'll generally need to make sure that you use them appropriately such that you don't have them overlapping each other entirely. Also, You never want to use sys.pushM plus $0. So that would be your index of 0 for these parameters, because PMAC uses that for some motor calculations and cases. It says here it's the default output register with motors with no hardware assigned. But it's a bit risky if you aren't sure that your motors are set in stone, all of them have hardware assigned, everything like that, because if you start using it and PMAC has a motor with no hardware assigned to it, it may use that register for some of its own calculations and therefore clear out your data or do its calculations based off your data. It will just mess things up in general, and it should be avoided. So you'd always want to start at some offset from sys.pushM. So in script, majority of the data conversions, typecasting, all that stuff is done for you. You may have inputs and outputs that are fixed point, Boolean, 16-bit, 32-bit, 64-bit. Depends on what kind of hardware you're using, how you're accessing the hardware, but it makes sense for using I/O. You may be trying to access it in many different ways. You could be trying to access the entire register as a single number, for instance, binary number, and then converting it from there. You could be accessing a whole array as a series of individual bits. This one is tied to this switch, this one's tied to that switch. You could be using outputs for large numbers, or you can be using outputs for individual status flags, or however you want to do it. There's a bunch of different options. So the PowerPMAC script environment does automatic type matching of different numerical points for you. It can do fixed point and floating point representations, and anywhere from 1-bit to 64-bit formats. All inputs are converted to 64-bit floating by default. All mathematical operations are done in this format for the highest amount of precision. If the calculation has a result, it is automatically going to be formatted into the correct format for that result. If you define an output as a double, for instance, and then you set a long equation and set that value equal to the double, it will automatically convert that value that it determines into whatever the type of the result is. If you define a result as an integer and then do a whole long equation and set that equal to that integer variable you defined, it will automatically convert the result into an integer for you. You basically don't need to worry about format conversions yourself. PMAC will pretty much take care of all of it for you, unless you're using the C language stuff. If you're using the C, you need to follow C language conventions of whatever sorts of casting C requires. If you're not using C though, you basically don't even need to worry about different formats. If you declare a variable to have a specific format, PMAC will conserve that and will make sure that it only has that format stuffed into it, but it will do its calculations in 64-bit floating point for the highest amount of accuracy that it can get. Now, for those calculations, we have a couple different operators and comparators. We have the standard arithmetic operators, plus, minus, asterisk for multiply, and slash for divide. Additionally, we have the percent sign for modulo. If you don't know what that is, it's basically the remainder of division. Normal rules of algebraic precedence apply. So PEMDAS, if you remember that, parentheses, exponents, multiplication, division, addition, subtraction. Additionally, for comparisons, there's bit-by-bit logical operators, a single ampersand, a single pipe, I think it is the vertical line, or a single caret is a bit-by-bit exclusive OR. You can additionally do a bit-by-bit invert. It's technically a function, however, it basically fits with these guys here. And you can do shifting if you want, so you can shift an entire value down or up a certain number of bits if you need to compare it with something else appropriately. If, say, you have a specific bit that's status flag and you want to check the value of it, you can shift your value up and down appropriately as to clear other bits and set that in the least significant or most significant bit. In addition to the bit-by-bit logical operators, there are conditional operators. 2 equals sign is equals. You'd use that if P1 equals P2, for instance, and that will return true if they are both equal. It will return false if they are not equal to one another. You can use exclamation mark equals for not equals to. You can additionally use the symbol here for approximately equals to. It's a bit of a weird one. Basically, we've defined a scope of 0.5. If it determines that two values are within 0.5 from one another, PMAC will say they're approximately equals. This is useful if you have floating point calculations and for whatever reason PMAC decides that one value is 64.9997325 and one of them is 65 outright. We know that because it's a computer, it may not give us an exact integer value for both of them, even though the equations that it's computing are the exact same. So there are times when you'd want to just use that approximately equals instead to see if they're close enough to one another. If you feel that 0.5 is too large or too small, you're welcome to scale the numbers you're comparing appropriately. If you multiply both of them by 10, that's the same as checking as they're within 0.05. If you divide both by 10, that's the same as checking as they're within 5. Again, similar to how we move equals, not equals, we have approx equals and approx not equals if they are outside of that range with respect to one another. Additionally, we have greater than and less than, and we have greater than or equal to and less than or equal to. We don't have not greater than, not less than, because not greater than is the same as less than or equals, and not less is the same as greater than or equal. We do have conditional combinatorial operators, 2 ampersands or 2 pipes for and or. And we do have a conditional negation operator, the exclamation mark, which is just not. So you use that one similarly how we have equals equals and exclamation mark equals. You can use that just as if it is not the value or if you do not want that value. Again, this one is just a good reference slide to have and hold on to when you're programming things, to know when to use equal sign versus equals equals and to know what your options are for various calculations. Standard assignment operators. So the general syntax would be variable, some sort of operator, and an expression, P7 equals 15. Or we saw with the pointer operator, M115 points to a memory location or something like that. So the expression is following the operator is evaluated during program flow, not at download or anything like that. Just as it's going through the program, when it gets to that point, it will compute the expression. The resulting value is immediately used and set to the value of the preceding operator. If a motion program is looking ahead due to blending, we'll learn about that. But basically, PMAC has this thing where it can blend moves together to make more seamless transitions between multiple different moves. That can be problematic, though, if you have a move command issued, then you have some calculations, then you have another move command issued, because PMAC will see the first move command and execute it, and then it will look ahead to try and find the next move command so that it makes sure that it's a good transition between the two of them. That means as far as the program flow is concerned, it will actually do a calculation between those two moves closer in time to the execution of the first one than the completion of the first move. If you want a calculation to occur at the beginning of the next move, you can use a synchronous M variable or a synchronous assignment, which we'll see in a little bit, such that it guarantees the execution of that equation is not occurring at program flow, but is occurring at beginning of the next line of motion. So if you're running an NC system and you want to have line numbers, you want to have line markers so you can see what line of code you're on, if you just issue a move and then P151 is equal to P151 plus 5, say you're incrementing by 5 for whatever reason every single time. If you do that, P151 will take the value of 5 higher sometime during the execution of the previous move. If you want to force it to happen, well, let me actually write it up here. If I have X10 P151 equals P151 plus 10, I'll say now. X5 P151 equals P151 plus 10, X0. If you just have it written out like this, you'll have X10, your x-axis will move out to a distance of 10 units. As it's moving, PMAC will begin to scan through your code, see, okay, this isn't a move command, but it's going to do this calculation. Then it'll see, okay, this is a move command, so I want to blend this move into this move here. The problem is, because PMAC is looking ahead through the code to see what the future things are, it sees this line and will execute that calculation sometime in the middle of this move here, likely closer to the very beginning of that move here. So your line marker will be ahead of what line is actually currently executing, because it will be incremented by 10 as if it's representing this line, even though we're still doing this move here. And then same thing here. If you use a synchronous variable definition, in that case instead it sees, okay, this is a synchronously defined equation. It's a synchronous variable declaration. So it's going to wait, and then it'll see this, okay, I'm blending x10 to x5. As soon as PMAC begins doing the x5 move, it will then calculate and set any synchronous defined variables. And we have a section on synchronous defined variables later on, so I'm not going to get into too much, but one simple example of why you'd want to use those would be line numbers in a motion program or an NC application or something like that. So for a simple assignment, you're just setting a variable of some sort equal to a value. You just set variable equals expression. Simple enough. We've all been doing it since second grade or so probably. You can also do an arithmetic option or operation, so plus equals, minus equals, multiplies equals. So my variable plus equals 5 is the exact same thing as my variable equals my variable plus 5. You can do logical operations, and equals, or equals, exclusive or equals, shift operations, increment, decrement, assignments. You have a couple different options if you want to do this. Beyond just simple expressions, you have a couple different choices of operators. Now, we also have some special representations, which are part of the IEEE 754 standard. PowerPMAC reports these values with the text shown here. It will show either INF or negative INF if you're doing something like a division by 0 that would result in a value of infinite or negative infinite. It will not create an error, but it will return that value. So if you look for that string in particular, you know, okay, I'm doing something wrong with dividing by 0. Positive infinite or infinity is going to be greater than any possible value in the whatever addresses, whatever registers you may have. Negative infinity is less than any finite number in a comparison also. So if inf greater than anything will always return true. If negative inf less than anything will always return true. Additionally, there is NaN, not a number. That's if you try and do a calculation that leads to an imaginary number, like square root of a negative value. Again, does not create an error. It just returns the value NaN. Sorry. Additionally, sometimes if you query something that doesn't exist, or it's a parameter that hasn't been initialized, or there's a couple of weird cases, you may see NaN being returned from those two. You can use the Boolean operator is NaN, is none, to check whether or not a parameter is set equal to NaN or not. Last, there is a -0 result you can get. That's obtained by underflow of negative values, and it's the exact same as 0 in any operations. If you do if -0 equals 0, that will return true. It's simply kept there as per that standard to let you know that you somehow have an underflow of negative values. Plus minus infinity and not a number is generally used just for diagnostics. You can check to see if those are the values you're getting, to see if you're dividing by 0 somewhere, or if you are using a function that has a domain error. The input you're giving into it isn't actually an acceptable input. It's best to check before an operation can produce such a response. If the result of something is going to be not a number, then set an error flag rather than doing the calculation, because if you're trying to determine motor positions and your calculation is going to return infinity, that's going to be a problem. So instead, you may do, if you think there's a chance they could do that, you can stick the whole thing in an if statement. If this is less than infinity, or if it's greater than some arbitrarily high number, then you know you have infinity or you don't have infinity, and you can either do your calculations or set an error flag and stop execution. That way you can come over to the machine later on, see, okay, that flag is high, somewhere in my calculations I have an error that's resulting in infinity. There's additionally some special script functions. You can do mmul, which is matrix multiplication, mmadd, matrix multiplication, and then adds the product to another matrix. M_inv inverts a square matrix. M_trans transposes a matrix. M_solves solves a simultaneous set of equations represented by a square matrix and a second vector matrix. Basically, we have a series of matrix manipulation functions you can use. We also have some vector manipulation script functions, vadd, vcopy, vscale, and we have some string manipulation, which is basically going to be the exact same string manipulation functions you have in C. So sprintf, stringcat, or stringcat, string copy, etc. Again, this one is just another good one to have for reference. If you ever want to use these, feel free to look them up in the software reference manual or in the interactive help in the IDE. It's just here so that you know they exist in case you ever want to use them.